Hello. In today's lesson, we will look at some thermal properties of matter. Now, what are the main properties of materials that will be affected by heating it? One of the most obvious properties of matter when heated is that objects generally expand when heated. So, thermal expansion is the most important property of thermal expansion. Now, when heat is supplied to a material, it increases its internal energy and causes the molecules to vibrate with larger and larger amplitude. What is the result of molecules vibrating with larger and larger amplitude? Well, when they vibrate with larger amplitude, they need more space to accommodate all these molecules. That means the object now expands. Now, as a result, each molecule now takes up a little more space and therefore causes the material to expand. As a result of expansion, its length, area, and volume will change. If I have a rod like this, if I hit it, its length can change, its volume can change, and if the object is a flat sheet of metal, for example, mostly its area will be increasing. So we will consider increase in length, area, and volume when an object is heated. We will consider each of them separately. So let's start with change in length of a rod like this when heated. Well, when an object is heated, its increase in length delta L. Now, this is the object at a temperature, at an initial temperature. We normally represent initial temperature as T0 and the final temperature as Tf. So, L0 is the length of the object at a temperature T0, and when the temperature increased, the length increased by delta L. Now, what are the factors on which the increase in length depend on? The increase in length, which is delta L, is proportional to its original length L0. It means you start with a bigger rod, the expansion will be greater. It is also proportional to the change in temperature delta T. So these are the two factors on which the increase in length delta L depend on. Can we write this as an equation? Well, I can write it as delta L equal to, remember, a proportionality sign can be replaced with an equal sign by adding a constant. So, the change in length delta L is proportional to the original length L0, and the increase in temperature delta T can be written as delta L equal to alpha L0 delta T, where alpha is a constant. Right. Alpha is a constant of proportionality, and we call it the coefficient of linear expansion, or sometimes it is called the linear expansivity. We will call it the coefficient of linear expansion. Now, what is it, how can you define? Can you define alpha? Now, alpha can be defined as the increase in length per unit length per Kelvin rise in temperature. If you take 1 meter of a rod and heat it by 1 Kelvin, how much is the increase in length? That is the value of alpha. That means there are different values of alpha for different substances. Now, alpha can be solved from here alpha equal to delta L over L0 times delta T. It is the increase in length per unit length per Kelvin rise in temperature. Tell me, what is the unit of alpha? If you notice, the unit of delta L is meter, the unit of L0 is meter, and therefore those will cancel. The unit of alpha therefore will be per Kelvin. The unit of alpha is per Kelvin. Well, a simple experiment can be done to measure alpha. You will be doing that in the lab. We will be using an equipment like this. Now, what does it consist of? Let me show you the equipment that we will be using in the lab here. Now, we have a steam jacket. This is called a steam jacket, and the metal rod whose alpha needs to be measured, coefficient of linear expansion, is this. Now, it is, first you measure its length L0, and then measure the room temperature, that is your T0. So measure the length L0 at temperature T0, and then insert this into the steam jacket so that one end of it is in contact with that screw there. In other words, it cannot expand that way. Now, we have a micrometer screw gauge arrangement here. By working it backward, I can allow space. Now, once the rod is inside, you work it forward, and once it is firmly in place, take the reading of the meter. Actually, that is your L0. You got your L0 by taking that reading. Now, work the screw back so that you have enough space over here. Work the screw back so that you have enough space between the rod and the screw. And then allow steam to pass through the steam jacket so that the rod gets heated. Now, when the steam has been passing for about 3 or 4 minutes, allow the steam to escape. Now, the temperature, once the steam passes for about 3-4 minutes, the rod will acquire that temperature, which can be measured by this thermometer. Once the expansion is complete, work the screw again forward until it is firmly in contact with the rod, and take the measurement again. The difference between the two readings will be your change in length delta L. Alright, let's put that away and do some calculations there. Alright, so the length of the metal rod L1 in place of L0, I'm going to call it L1, is measured at the temperature T1, and in this arrangement shown, as I have told you, you measure the length L2 at temperature T2 by passing steam through the steam jacket. Now, therefore, delta L will be L2 minus L1, and delta T will be T2 minus T1, and therefore alpha equal to delta L over L1 times delta T. Is that right? Increase in length divided by original length times the rise in temperature. Now, I'm going to write delta L as L2 minus L1. Is that right? Okay, now I have written it like this so that I can now obtain an expression for L2 in terms of L1 and alpha. That is, L2 minus L1 equal to alpha times L1 times T2 minus T1. Can you solve this equation for L2? Move L1 to the right and then factor out L1. So, move L1 to the right, you get L2 equal to L1 plus alpha L1 times T2 minus T1. factoring out L1 gives me L2 equal to L1 times 1 plus alpha delta T. Now, once that equation is there, we can now find the length of a rod like this at any given temperature, because delta T is the change in temperature, as long as you know its initial length and the coefficient of linear expansion. Alright, let's now talk about change in area. Similar expressions can be written for change in area with temperature as follows. Delta A, increase in area, is proportional to the original area and the rise in temperature, and therefore delta A equal to beta A delta T. What will you call that constant beta? It's the coefficient of area expansion. So beta is the constant of proportionality and is called the coefficient of area expansion. And what is it a measure of? It is a measure of the increase in area per unit area per Kelvin rise in temperature, and its unit also is per Kelvin. Now, the coefficient of area expansion beta can be calculated just like we calculated the coefficient of linear expansion. We can calculate the coefficient of area expansion beta as delta A divided by A times delta T. And delta A is A2 minus A1. Is that right? The change in the area. And this equation can now be used to solve for A2, the final area, like this. A2 equal to A1 times 1 plus beta times T2 minus T1. So, once you know your initial area, the coefficient of area expansion, and the change in temperature, we can find the area at that final temperature. So, since an area is made up of two lengths, is that right? If you take any object like this, area is made up of a length and a width. Well, a width is also a length. So, since area is made up of two lengths, you can write an approximate relation between alpha and beta. You see, area involves change in length in two ways. Therefore, what do you think is an approximate relation between alpha and beta? Anybody tell me? Well, beta will be approximately 2 times alpha. Why? Because a change in area involves a change in length and another change in length. So, the coefficient of area expansion is approximately 2 times the coefficient of linear expansion. Now, similarly, let's consider change in volume. Similar expression can be obtained for change in volume as delta V equal to a constant gamma times V delta T. The change in volume is proportional to the original volume and the change in temperature, where gamma is a constant and we call it the coefficient of volume expansion or coefficient of cubical expansion. And what is it? If I ask you what is the definition of volume of cubical expansion, what is it? Volume of cubical expansion gamma is a measure of the increase in volume per unit volume per Kelvin rise in temperature. And what is the unit in which gamma is measured? It is measured the same unit per Kelvin. Well, we can write gamma equal to delta V over V delta T, and delta V is V2 minus V1. So it can be written now as V2 minus V1 divided by V1 T2 minus T1. I just wrote in place of V, V1. And can you solve for V2 from there? Therefore, V2 equal to V1 times 1 plus gamma T2 minus T1. So we have now three equations: increase in length, increase in area, increase in volume. Now keep those equations with you. That will come handy when you want to solve problems. Alright, since volume is made up of three lengths, is that right? Volume is length multiplied by width multiplied by height. Is that right? If you want to find the volume of something like this, it will be length multiplied by width, the length multiplied by width multiplied by height. So a change in volume involves a change in three lengths. Therefore, what is an approximate relation connecting gamma and alpha? Gamma and alpha are connected as gamma equal to 3 alpha. Well, let's now write down that approximate relations. Assume that each of the following objects is heated by 1 Kelvin so that delta T equal to 1. Now here we have a rod of original length L0 is heated by 1 Kelvin, therefore delta L divided by L0, is that right? You have increase in length per unit length per Kelvin rise of temperature. This time the temperature increase is 1 Kelvin. So delta L divided by L0 will be alpha. Delta A divided by A0 will be 2 alpha. Is that right? And delta V divided by V0 will be 3 alpha. So approximate relations connecting alpha, beta, beta equal to 2 alpha, and gamma, gamma equal to 3 alpha. Alright. Let's now have a look at some values of alpha and gamma of some common materials. Again, print this out from the PowerPoint I provided so that you can use them for solving problems. We will be using mainly aluminum, brass, copper and so on. So those values will be important. The coefficient of linear expansion for aluminum is 24 times 10 to the negative 6 per Kelvin. Alright? So keep these values with you. Let's now talk about change of density with temperature. Well, when you heat an object, its volume increases. Well, will the mass of the object increase? Well, the mass doesn't increase, only the volume increase. That means the original mass is now distributed into a larger volume. That means mass per unit length will now decrease. So when you heat an object, its density will decrease. When an object is heated, its mass remains the same while the volume increases. As a result, the density decreases with temperature. Well, there are many applications for that phenomenon. When you heat an object, density decreases. Have you watched when you heat water, the water that gets heated will rise. Now, why does it rise? Because the hot water is less denser than cold water, so the hot part will rise. We will talk about that a little later. Now, consider an object of mass m kilogram. If V0 is the volume and D0 is the density at 0 degrees Celsius, then I can write D0 equal to m over V0. Is that right? Mass divided by volume is density. Now, therefore, m equal to D0 times V0. Alright. And suppose you heat that object to a temperature T degrees Celsius. What will be the volume? The volume at that temperature will be Vt. and the density at that temperature will then be dT equal to mass divided by Vt. Now, will the mass change because you heated it? No, the mass does not change. So, your density at 0 degrees Celsius, if you remember, it was d0 equal to m over v0, or we obtained m equal to d0 v0. Now from here I can write m equal to, now this m I'm going to replace by d0 v0. You remember why I replaced it? Because previously we said, let me go back and write that down for you. In the previous slide, we had this. d0 equal to m over v0. Therefore, m equal to v0 d0 or d0 v0. So, this m is the same as this m. M hasn't changed. So, I replace that m by d0 v0. What happens now? V0 and V0 will cancel. As a result, what is our expression now? That will be dT, density at any temperature, is d0 divided by 1 plus gamma delta T. Now, using binomial theorem, well, I don't know how many of you have seen binomial theorem. Well, I'm not going to go into it. But I can use binomial theorem and write this as an approximation as dt equal to d0 times 1 minus gamma delta t. I want you to remember that equation. The density at any given temperature is density at 0 degrees Celsius times 1 minus gamma delta t. What is gamma? Gamma is the coefficient of volume expansion, which is approximately 3 times the coefficient of linear expansion. And delta T is the change in temperature. Let's do an example. As a steel rule has a length of 30 centimeter at 20 degrees Celsius, what is the length at 100 degrees Celsius? Alpha for steel is 11 times 10 to the negative 6 per Kelvin. A straightforward, very simple problem. Pick out our data. L1, the original length is 30 centimeter, that is 0.3 meter. The change in temperature delta T is 100 degrees Celsius minus 20 degrees, that is 80 Kelvin. I hope you are not confused by this usage Kelvin. Remember, temperature intervals, whether you use degrees Celsius or Kelvin, intervals are the same in Celsius and Kelvin. So 100 degrees Celsius minus 20 degrees Celsius is 80 Kelvin. And alpha is given to us. Therefore, we go back and use that equation. You remember I told you to remember that equation? L2 equal to L1 times 1 plus alpha delta T. Now, replace all these with their values. L1 is 0.3 meter, alpha is 11 times 10 to the negative 6, and delta T is 80. And calculate that on your calculator. That gives me L2 equal to 0.30026 meter. So what is the increase in length therefore? You started with 0.3 meter, your final length is 0.30026 meter, and therefore the increase in length is this minus that, about 0.3026 meter. Another one. A bridge 100 meter long is built of steel. By how much will its length change from the coldest winter of negative 30 degrees Celsius to the hottest summer days of 40 degrees Celsius? Well, we have delta T, the change in temperature. We have the initial length. We need to find the change in length, right? L1 equal to 100 meter. Delta T is the final temperature minus the initial temperature. 40 minus negative 30, that is 70 Kelvin. Alpha for steel, I haven't given it to you here, but we can use that anytime. That's the value for alpha. So delta L equal to alpha L delta T. Here L stands for L1. So we know alpha, we know L, we know delta T. Therefore delta L equal to, how much is that equal to? It's 0.077 meter. Another example. The density of aluminum is 2.7 times 10 to the 3 kilogram per meter cube at 0 degrees Celsius. What is the density of aluminum at 200 degrees Celsius? Again, a direct application of that formula. Density at 0 degrees Celsius is known. Change in temperature, well, the change in temperature is 200 minus 0, that is 200 Kelvin. And gamma for aluminum. You see, alpha for aluminum is 24 times 10 to the negative 6. That's what is given. Therefore, gamma will be 3 times alpha. So, dt equal to d0 times 1 minus gamma delta t. We know d0, we know gamma, we know delta t. Put in all those values and use your calculator now to simplify this. Make sure you can do these kind of calculations without making a mistake on your calculator. Alright? So that will be 2.66 times 10 to the 3 kilogram per meter cube. You can see there is a substantial change in the density when the temperature increased. Okay, another example. A hole is drilled in an aluminum plate with a steel drill bit which has a diameter of 6.24 centimeter at 20 degrees Celsius. In the process of drilling, the temperature of the drill bit and the aluminum rose to 168 degrees Celsius. What is the diameter of the hole in the aluminum plate when it has cooled down to room temperature? Well, when the temperature of the drill bit increases, the diameter of the drill bit will increase. That means when you finish drilling the hole, the diameter of the hole is bigger than when it is cooled down. Is that right? Yes. So we need to find that diameter. So how do we now start this problem? Well, we know the diameter of the aluminum at 20 degrees Celsius. I used that D for diameter. Remember, diameter is the length. So diameter of the drill bit, the diameter of the drill bit is 6.24 centimeter, which is 0.0624 meter. The change in temperature is 168 minus 20, 148 degrees Celsius. And alpha for steel, is that right? We need the alpha for steel is 11 times 10 to the negative 6 per Kelvin. So the diameter of the hole at 168 degrees Celsius is the diameter of the drill bit at that temperature. So remember, we are not finding the diameter of the hole now. We are finding the diameter of the drill bit at the higher temperature. That's why we are using alpha for steel. So that will be, since the diameter is a length, I can write D2 equal to, remember the D there stands for a length, or you can read it like this, L2 equal to L1 times 1 plus alpha delta T, where that L2 is the diameter at the higher temperature L1 is the diameter at the lower temperature. We will use D2 and D1 for the diameter. Now, we know the diameter at 20 degrees Celsius. We know alpha for steel and we know delta T. So, we can now find the diameter of the drill bit at 168 degrees by substituting those values. What does that give you? That will be 0.0625 meter. That is the diameter of the drill bit. Therefore, what is the diameter of the hole that is drilled on the aluminum sheet? It's the same thing. Okay, the diameter of the aluminum hole at that temperature is therefore the same. That is 0.0625 meter. Alright, now this is the diameter of the hole at 168 degrees. And now the aluminum is going to cool down to 20 degrees. We need to find the diameter of the hole at that lower temperature. So look at the assumption I've made. If dA1 is the diameter of the hole at 20 degrees Celsius and dA2 is its diameter at 168 degrees, again they are lengths, is that right? Each of this is a length. dA2 now stands for L2, the length at 168 degrees, and dA1 stands for L1, the length at 20 degrees Celsius. So I can write dA2 equal to dA1 times 1 plus alpha aluminum this time, because we are now considering the aluminum sheet, times delta T. This is the same as L2 equal to L1 times 1 plus alpha delta T. Well, dA2, the diameter of the aluminum hole at 168 degrees is this, we calculated. dA1 we don't know, that's what we need to calculate. And alpha aluminum is this, and the change in temperature is 148 Kelvin. And therefore, calculating what is inside the parenthesis gives me 0.0625 equal to 1.00355 dA1. This quantity gives me 1.00355. And therefore, what is dA1 equal to? Well, this divided by that, that's 0.0623 meter. This is the diameter of the hole when it has cooled down to 20 degrees Celsius. Well, what was the diameter at the higher temperature? 0.0625. So tell me, has the diameter of the hole become smaller or bigger when the aluminum sheet cooled down? Well, it has become smaller. So think about this. An aluminum sheet with a hole at the center is heated to a higher temperature. Will the hole become bigger or smaller? Okay, I want you to write about it and email it to me. Alright? That will be an extra credit point. An aluminum sheet with a hole at the center is heated to a higher temperature. Will the hole become bigger or smaller? Now, in order to earn the extra credit point, the answer is not just this way or that way. You give me the answer and justify why. Why do you think it happens that way? I want to see 3 or 4 sentences written, and then only you will get the extra credit points. Alright? Let's move on. Let's now talk about transfer of thermal energy. What are the mechanisms by which thermal energy gets transferred from one place to another? Now, I'm sure you have heard about thermal energy transfer. What are the main mechanisms of heat energy transfer? Well, there are 3 main ways. There are 3 main mechanisms by which heat energy gets transferred from one place to another. They're called conduction, convection, and radiation. Now we will look at each of these separately. Conduction. What is the process of conduction? Conduction is to conduct heat, to pass heat from one to the other. Just like if I want to pass a box of chocolate to everybody in the room, I put the chocolate here so that the first student takes one and passes it on to the next until it reaches the last student. In the same way, if I put this aluminum rod in hot water, heat is received by molecules that are in contact with the hot water, then gets passed on from molecules to molecules until it reaches the other end. That is conduction of heat. So, conduction is a mode of heat transfer within an object due to the interaction between atoms and molecules without involving their bodily motion. In fact, the student here is not moving away to supply the chocolate. What happens is the chocolate simply moves from student to student. Heat simply moves from molecule to molecule. Actually, heat transfer conduction in metals is much more complex than that, because metals have free electrons and they play a crucial role in transferring heat from one end to the other. And that is a very complex phenomenon for us, so we will not discuss that in here. Conduction in metals is specially assisted by the motion of electrons which carry thermal energy from one part of the conductor to another, because it contains a lot of free electrons. As energy is passed on from molecule to molecule or atom to atom, heat travels progressively from one end of the conductor to the other. And this method of heat transfer is called conduction of heat. Alright, the figure shows a section of a conductor of length delta x through which heat is flowing. Now here is the section of a conducting material of length delta x, area of cross section A. One end is at a higher temperature theta 1, the other end is at a lower temperature theta 2. That means heat is going to flow from the hot end to the cold end. Tell me, what are the factors on which the rate of heat flow depend on? Well, you can see the heat flows from the hot end to the cold end. From the hot end to the cold end. The temperature at one end is theta 1 and the temperature at the other end is theta 2. The drop in temperature delta theta is theta 1 minus theta 2. It is not theta 2 minus theta 1 because theta 2 is a lower temperature. So that's the drop in temperature. What is the temperature gradient? What is the meaning of a gradient? A gradient is a rate of change. Is that right? Yes, a rate of change. If you work and earn $10 an hour, that $10 is a rate of change. It is the gradient of the graph between, if you draw a graph of amount of dollars against time, 10 will be the slope of that graph, the gradient, the rate of change. For every hour you earn 10 more dollars. So what is the temperature gradient here? The temperature gradient will be increase in temperature per unit length. How do you calculate that? Now the increase or decrease, drop in temperature, because as you move from the hot end to the cold end, the temperature is dropping. So temperature gradient is a measure of the drop in temperature per unit length. The drop in temperature is theta 1 minus theta 2. And the drop happens in a length delta x. Therefore, delta theta divided by delta x is called the temperature gradient. the drop in temperature per unit length. And that is theta 2 minus theta 1 over delta x. And that's a very important concept. Alright. Now, the rate of heat flow, I asked you this question. The rate of heat flow depends on what factors? The rate of heat flow is written like this: delta Q divided by delta T. The rate at which heat is flowing. What are the factors on which the rate of heat flow depend on? Is directly proportional to the area of cross-section A. In other words, if heat is passing from this end to that end, this is the area of cross-section. Now, if the area is greater, more heat will be able to pass through it. So the rate of heat flow is directly proportional to the area of cross-section, and also it is directly proportional to the temperature gradient. That means if the temperature difference is greater, heat will flow at a faster rate. That's not difficult to understand. Now, if the difference between the temperature on these two ends is 100 degrees Celsius, the heat will flow from one end to the other much faster than if the difference in temperature is 10 degrees. So, the rate of heat flow is directly proportional to the temperature gradient. So, what are the two factors on which the rate of heat flow depend on? The rate of heat flow is directly proportional to the area of cross-section, and also it is directly proportional to the temperature gradient, the fall in temperature, the drop in temperature per unit length. Or we write it as an equation: the rate of flow of heat, delta Q by delta T, equal to Ka delta theta by delta x, where this K is a constant. We change the proportionality to an equation by adding a constant. And that K is a constant, and it is called the thermal conductivity of the material. So K is the constant of proportionality and is called the thermal conductivity of the material. Now, is it possible for you to figure out the unit for this K? Unit for K. Let's figure out the unit. Tell me, what is the unit for thermal, the rate of flow of heat? Delta Q by delta T. Let me see if anybody can tell me that. What is the unit in which heat is measured? Delta Q. That's a measure of heat. Heat is measured in joules. Time is measured in seconds. So delta Q by delta T is measured in joules per second. Let's write that down. Delta Q by delta T is measured in joules per second. Alright? So, the rate of flow of heat. Now, it is sometimes called thermal current. You see, any rate of flow is called a current. The rate of flow of air is air current. The rate of flow of water is called water current. The rate of flow of electric charge is called an electric current. The rate of flow of heat is called thermal current. So, this quantity is thermal current. What is the unit for measuring thermal current? Joules per second. Alright, tell me, what is the unit for measuring area? It's of course meter squared. But before that, tell me, what is joules per second equal to? You're familiar with it. Joules per second is the unit of power. Work done per second is a watt. So joules per second is a watt. So what I'm going to do is I'm going to cut this off and write watt there, because joules per second is a watt. So the unit of thermal current is the watt. Now tell me, what is the unit of area? Area is meter squared. Alright, so area is meter squared. What is the unit of delta theta over delta x? Delta theta is Kelvin, delta x is meter, so delta theta by delta x is Kelvin per meter. Now look at the way. I want you to give me the unit of K. What is the unit of K? Now you know the thermal current is measured in watt, and now this meter and this meter will cancel, and therefore K will be measured in, what's this? Watt per meter Kelvin. Because this meter and this meter will cancel, and if you divide by meter Kelvin, watt per meter Kelvin is the unit of K. I hope you understood how I got this. The unit of K, thermal conductivity, is watt per meter Kelvin. Alright, let me take you back to here. So, K is measured in watt per meter per Kelvin. That is the unit of thermal conductivity. And here I have given you a table of values for thermal conductivity for various materials. And if you do lab on this campus, there is a lab we will be using to measure the thermal conductivities of various materials like this. So again, print out these from the PowerPoint and keep it with you so that you can use it for solving problems. The values of thermal conductivities of common materials measured in watt per meter per Kelvin. Alright. Now, you recognize this equation? Delta Q over delta T. What did I say this is called? The rate of flow of heat is called thermal current, equal to Ka delta theta by delta X. What is delta theta by delta X called? The temperature gradient. Alright, so delta Q by delta T is called thermal current, and we're going to represent the thermal current by the letter I. So from now on, the quantity delta Q by delta T will be represented by I. Tell me, what's the unit for thermal current? Forgot? Unit of thermal current is the watt. So thermal current I is measured in joules per second, which is the watt. So I can now write I equal to Ka delta theta by delta X, or delta theta equal to I times delta X divided by Ka. Now I have colored delta X divided by Ka red because that quantity has a special significance. The quantity delta X divided by Ka is called the thermal resistance. How good a material is in resisting the flow of thermal energy through it. Thermal resistance, and I'm going to represent that by R. Alright, so take note of this. The quantity delta X divided by Ka is called the thermal resistance R. So look at the equation we have. Delta theta equal to I times R, where I is the thermal current, which is delta Q by delta T, and R is the thermal resistance, which is delta X divided by Ka. Alright? So R equal to delta X divided by Ka is called the thermal resistance of the material. And that R is measured in Kelvin per watt. You can figure it out from there. Now, delta X divided by K, look at that. Delta X divided by K, without using that A, is actually called the R value of the material. Now, if you are familiar with building construction material, Very often you buy materials for insulation. What is an insulator? An insulator is something that will not allow thermal energy to pass through it very easily. And all such materials has a thermal resistance value, right? But very often when you go to the shop to buy an insulator, the material is not rated for the thermal resistance, but it is rated for something called the R value. Now, R value is not the resistance. The R value is delta X divided by K. So the R value determines how good an insulator the material is. Alright, so next time you go to buy an insulating material, look for its R value. It is delta X divided by K. Notice here that R value is not the same as the thermal resistance R. The thermal resistance is delta X divided by Ka. The R value is simply delta X divided by K. Okay. Now, very often we combine thermal resistors in either series or parallel. Now, look at this. Here I have two thermal resistors combined in series. That means thermal energy has to pass through both to reach the other end. That means you are increasing the thermal resistance. Is that right? So, when thermal resistors are combined like this, the total thermal resistance will be the sum of the two resistances. R equal to R1 plus R2. On the other hand, if they are arranged in parallel like this, well, that means heat energy can either pass through here or here. You are actually reducing the resistance to flow. Is that right? In that case, if R is the total resistance, then 1 over R equal to 1 over R1 plus 1 over R2. Well, just leave it there. If you need it, we will use it. Okay, let's go and do a problem now. A copper bar 2 meter long has a circular cross section of radius 1 centimeter. One end is kept at 100 degrees Celsius and the other end is kept at 0 degrees Celsius. The surface of the bar is insulated. The surface of the bar is insulated so that no heat will escape through that surface. That means all the heat that is passing from here will pass through that way. No heat energy will be escaping on the surface. Now find the thermal resistance of the bar, the thermal current, the temperature gradient, and the temperature of the bar 25 centimeter from the hot end. Alright, this is the copper bar. Delta X, the length is 2 meter. The temperature at the hot end is 100 degrees Celsius. Temperature at the cold end is 0 degrees Celsius. So that delta theta is 100 Kelvin. Now, the radius of this is a rod like this. The radius is 1 centimeter, which is 0.01 meter. Now, what does that help you to do? We can now calculate that area. Now, if the radius is 0.01 meter, can you tell me what is that area of cross-section? Well, we can calculate that. And this is a copper material. K for copper from the table is 401 watt per meter Kelvin. So, the area of cross-section is pi r squared. Is that right? And this is the radius. So that will be pi times 0.01 squared is 3.14, that is approximate value of pi, times the radius squared, and that will be, this is the area of cross-section there. Now, we first want to find the thermal resistance. Anybody tell me what's the equation for thermal resistance? Yes? Thermal resistance is delta theta divided by K delta X divided by Ka. Is that right? So R, the thermal resistance is delta X divided by Ka. Delta X is 2 meter, K is 401, and our A, area of cross section, is this we calculated. So what is R equal to? 15.88 Kelvin per watt is the thermal resistance. We now need the thermal current. What is thermal current? Delta Q divided by delta T, which is called I. And how is the thermal current related to the thermal resistance? I equal to, well, delta theta equal to I times R. Can you recall that equation? Alright. Delta theta equal to I times R, where delta theta is the difference in temperature, I is the thermal current, R is the thermal resistance. Therefore, I equal to delta theta divided by R. We calculated thermal resistance, we know delta theta, therefore I equal to 6.3 watt. The thermal current is 6.3 watt. What's the next we want? The temperature gradient. The temperature gradient is delta theta divided by delta X. Is that right? So temperature gradient is delta theta divided by delta X. Delta theta is 100 Kelvin. Delta X is 2 meter. So that will be 50 Kelvin per meter. What is the next thing we need to calculate? We need to find the temperature, well, the temperature gradient is this. We need to find the temperature 25 centimeter from the hot end. So, what is the temperature 25 centimeter from the hot end? This is 2 meter, and that is 1 meter. So 25 centimeter will be somewhere here. Now tell me, what is the temperature gradient? 50 Kelvin per meter. What does it tell you? It means for every meter you go, the temperature will fall by 50 Kelvin. So, if you go from here to 1 meter, the temperature will fall by 50 degrees Celsius. So, what will be the temperature at the middle of the rod? 100 minus 50, that will be 50 degrees Celsius. Tell me, if the temperature gradient is 50 Kelvin per meter, if you go half a meter, how much will be the fall in temperature? If you go half a meter, the fall in temperature will be 25 degrees Celsius. So, if you go half a meter from here, the temperature will be 25 degrees less than this. Alright. Now, how much will be the temperature if you go 25 centimeter, a quarter of a meter? When you go a quarter of a meter, the temperature will fall by a quarter of 50, which is 12.5. So, you can see I'm doing it mentally. The temperature will fall at that 25 centimeter mark, how much? 12.5. So, the temperature there will be 100 minus 12.5 will be 87.5 degrees Celsius. Let's write that down. So, temperature 25 centimeter from the hot end is theta equal to 100 minus, is that right? For every meter, the drop is 50 Kelvin. Therefore, for 25 centimeters, 0.25 centimeters, the drop will be 50 times 0.25. So that will be 100 minus 12.5, 87.5 degrees Celsius. You can do it by simple argument. Okay, now I'm going to stop this one here as my tape is running out. I will do one more problem of this in the second part of this lesson, and I will complete the lesson by a discussion on convection and radiation. Alright, I will see you for that part of the lesson later on.